within this linkage, there are two main goals. The first is to determine what the spectrum of mineral deposits are in the Gawler Craton related to the 1590 million year old magmatic hydrothermal event, and also to create a prospectivity map in order to reduce risk and optimise mineral exploration in the Gawler Craton. In order to do this, we need to understand the fundamental processes that control the formation of ore deposits and also their preservation. And one of the processes important to this is the role of magnetism, and so that's where my contribution comes into this linkage project. So specifically, looking at how we can use magmatic rocks and their chemistries as proxies into understanding the composition of the crust and the mantle. So this talk will focus on using mafic igneous rocks in order to understand what the composition of the mantle was at 1590 and how this may relate to mineralisation. So in the Gawler Craton we have two main mineral provinces, the ICG province in the eastern Gawler and the central Gawler gold province. These are both display a clear spatial relationship with the Hildeper suite, and in most cases there is an association with the mafic component of that Hildeper suite. So in order to better understand what this relationship is, we want to try and understand what the composition of the mantle is, so that we can maybe better predict where we might be able to find other mineral deposits and also understand how they formed. What we'll find is that the composition of the mantle at 1590 was heterogeneous, and that there are at least 4 different compositional groups that we can define from this based on their geochemical affinity, and that we interpret them to have resulted from the partial melting of a metasomatized subcontinental lithospheric mantle. And so then that begs the question of what the role of a metasomatized subcontinental lithospheric mantle might be in the generation of the copper and gold mineralisation in the Gawler Craton. So previous work, particularly in the ICG province, has shown that there is a increasing mantle input with mineralisation, particularly, first established at Olympic Dam back in the mid-90s. And so from these studies, it was then suggested that there was this important connection between the mantle and mineralisation. This has been later confirmed by geophysical studies. So here we have magnetotellurics, which show clear conductivity pathways between the lower crust and mantle, linking towards 3 of the main ICG deposits in the Gawler Craton. And so here we're getting, confirmation from the geochemistry and the geophysics, suggesting that we've got this important mantle input. More recently, earlier this year, Roger Skiro and others compiled all of the available geochemical and geophysical data to essentially create this sort of mantle domain map, and they identified a metasomatized subcontinental lithospheric mantle zone, which lies under a significant portion of the Gawler Craton. The MT data also has shown that the lithospheric mantle beneath the Gawler Craton is hydrous and metasomatized. But one of the limitations with the geochemical data in particular is that a lot of these studies have been isolated. There hasn't been much comparison between individual studies, and a lot of them are restricted to particular geographical areas. So there's been a lot of information from the eastern Gawler and not so much from the central Gawler. So we therefore saw an opportunity to collect as many mafic Hildeper suite rocks as possible to get a wide geographical representation of the mantle at that time. And so in this sense, there hadn't really been a systematic approach to mapping the composition of the mantle. So this is essentially the field area that I was focusing on, and trying to collect as many samples from those little green blobs as possible. Understandably, because we're dealing with a large geographical area, their geochemical compositions are quite variable. Because we're interested in the mantle, we can apply a simple filter just by filtering by silica and magnesium contents, so that we can be fairly confident that we're dealing with primary geochemical signatures and to remove the most obvious signs of crustal contamination as possible. Within this remaining data, we then see the emergence of these 4 compositional groups, which I'll now run through individually. So group 1 occur in only 3 areas, 1 in the ICG province and 2 within the central Gawler province. This group is distinguished by flat trace earth elements, and they also have low thorium-niobium ratios and what we call juvenile epsilon neodymium values. So these are more typical of being derived from the mantle. So in neodymium space, generally anything that's above 0 is considered to be a mantle signature, and we call that juvenile, and anything which has a negative value is more typical to be derived from the crust. When we look at group 2, they appear to only be in the northern portion of the sample, of the study area. They also have these sort of flat to moderate trace and rare earth elements, but are perhaps a little bit more enriched than group 1, suggesting that we're looking at probably some kind of different mantle source. These variations are also reflected through slightly higher thorium-niobium ratios and also quite variable epsilon neodymium. So it's interesting to note that the most negative values actually occur in the ICG province, and the more juvenile values occur in the central Gawler province. Group 3 represent the most regionally extensive of all these groups, occurring in almost every location where we collected a sample from, and these are distinguished by their quite steep trace earth and trace earth element patterns. You can see there's a dashed reference line there, which is the upper continental crust, and the patterns of these rocks actually resemble quite crustal signatures. These are also reflected by high and variable thorium-niobium ratios and also variable neodymium ratios. Group 4 have only been identified in 2 locations in the northern part of the study area, and they look quite similar to the previous group, except that they are exclusively have these quite negative epsilon neodymium values. So what this sort of brings us to is we've got these mafic rocks that are presumably derived from the mantle, and we need to try and reconcile why we see these crustal signatures in these rocks and try and explain why we have such a variation in these epsilon neodymium values and also their trace and earth element signatures. And so one way of doing this is using things like source component diagrams, and here we're using the thorium-niobium ratios as an input for a crustal component, and this could either be something that's been previously subducted and stored within the subcontinental lithospheric mantle, or it could represent crustal contamination. But because we tried our best to eliminate crustal contamination, we can interpret these as representing a subducted component in the subcontinental lithospheric mantle. So this is shown by increasing thorium-niobium on the y-axis. So here we have different mantle domains that are defined by these 2 proxies. So when we start to look through what each of these groups represent, we can see that group 1, with their low thorium-niobium ratios, they sit within these quiet mantle domains. So they might be similar to something derived from an enriched mid-ocean ridge basalt, or perhaps even an oceanic island basalt. And this is consistent with those flat trace earth elements and their high epsilon neodymium values. Group 2 sort of sit in the middle of nowhere. They don't really fit in any of these boxes on this diagram, but perhaps they represent a separate mantle source that is still an enriched mantle, but separate from the previous. Group 3 sit almost entirely within the subduction modified lithosphere, and this is also consistent with what we see in their whole rock and isotopic signatures. And then group 4 are mostly within this field, but with their negative epsilon neodymium values, they may actually represent some additional crustal contamination. So despite our best efforts to remove it, the isotopic data might actually be suggesting that there has been some additional crustal material to this group. So now if we start thinking about processes that might create such a heterogeneous mantle, we can think back to the geological history of the Gawler Craton. It's got quite an extended geological history, and it's possible that there have been previous metasomatic events related to subduction or subduction-like processes that have affected the composition and the structure within the subcontinental lithospheric mantle. It's possible that during one of these subduction events that the fluids derived from that subducting slab have created metasomatized components. Some of these may have broken away and then become isolated and stored within the subcontinental lithospheric mantle. And then when we move to time 1590, we apply a heat source through a stenospheric upwelling, which may be a result of mild extension related to the Gawler Range volcanics or the mafic underplating of a mantle plume. In any case, we add heat, which induces partial melting, and it's possible that each of these groups may represent zones such as these within that mantle structure. So where the enriched basalt group is derived from, we see little interaction with a previously metasomatized subcontinental lithospheric mantle, and this may be more reflective of perhaps that mafic underplating related to a mantle plume, whereas each of the other groups may represent various components stored within the subcontinental lithospheric mantle, and particularly with that group 3 representing perhaps the largest preserved zone of that metasomatized mantle. It's possible that these previous subductions events are mechanisms to create copper and gold-rich zones within the subcontinental lithospheric mantle, and so it's possible that when these mafic rocks were partially melted, that if they were hydrous and fertile, they're capable of remobilising copper and gold into the upper crust and potentially forming the iron oxide, copper gold and gold mineralisation that we see in the Gawler Craton. This is still something that we're working through, and this is just one of the ideas that we're putting out there for this model. So where to next? Where are we heading after this? So as I previously mentioned, we're also interested in the composition of the crust, and so we can use the Felser-Kildeber suite to help with constraints on this. And one of the curious things about the Felser-Kildeber suite is that they have this extreme rare earth element concentration. We can see here with Olympic Dam, Oak Dam and Emmy Bluff all having these quite extreme neodymium concentrations. And so the next chapter will be beginning with Hillside, and we'll see where this will take us. Thank you.